Basic refrigeration involves the process of removing heat from a space or substance to lower its temperature. This is achieved using a refrigeration cycle that circulates refrigerant through various stages to absorb and release heat. The fundamental principles of refrigeration include compression, which is the refrigeration cycle starts with the compressor. The compressor takes low pressure, low temperature refrigerant gas and compresses it, raising both its pressure and temperature. This compressed gas is now at a high pressure, high temperature state. Second would be condensation. The high pressure, high temperature refrigerant gas then flows into a condenser. In the condenser, the refrigerant releases the heat to the surrounding air or water. This causes the refrigerant to condense into a high pressure liquid. The next phase is expansion. The high pressure liquid refrigerant moves into an expansion valve, capillary tube, or piston. This valve allows the refrigerant to expand rapidly, reducing its pressure and causing it to cool down significantly. The fourth area is evaporation. The now cooled low-pressure refrigerant enters the evaporator. In the evaporator, the refrigerant absorbs heat from the area or substance being cooled, causing it to evaporate and turn into a low-pressure vapor. After that, it returns to the compressor, where the cycle begins all over again. The continuous cycle of compression, condensation, expansion, and evaporation allows the refrigerant to extract heat from one location and release it into another. As a result, the temperature of the cooled space or substance is reduced, creating a cooling effect. Refrigeration systems can be found in various applications, including air conditioning units, refrigerators, freezers, industrial cooling processes, and more. Different refrigerants and variations in the cycle may be used depending on the specific application and efficiency requirements. Temperature pressure charts are used to show the correlation of temperature and pressure of refrigerant. If you look at the example on the screen, a cylinder of refrigerant, in this case R22, at 40 degrees will have a pressure of 69 psi. This doesn't matter if it has 1 ounce, 5 pounds, 10 pounds, the pressure will be 69 psi. The charts are based on saturation properties for which a refrigerant evaporates and condenses. A refrigerant charging manifold is a tool used to measure and regulate refrigerant levels in a system. It consists of two pressure gauges, one for high pressure, which is discharge or head pressure, and one for low pressure, which is suction or evaporator pressure, along with the valves and hoses for connecting to the refrigeration system. Here's how you can read the gauges on a refrigerant charging manifold. Step 1 is you identify the high and low pressure gauges. The gauges are usually color-coded or labeled, with the high pressure gauge as red and the low pressure gauge as blue. Make sure you correctly connect the hoses from the manifold to the corresponding high and low pressure ports on the refrigeration system. Step 2 is the pressure units. The pressure gauges display pressure in PSI or pounds per square inch. Ensure you know which unit of measurement your gauge is using. Sometimes they also will display in bar. Step 3 is system status. Ensure the refrigeration system is running and stabilized. The pressures will vary depending on the system's temperature and load conditions. Step 4 is reading the high pressure gauge. This gauge measures the pressure of the refrigerant leaving the compressor and entering the condenser. The pressure indicated on the high pressure gauge will vary depending on the type of refrigerant, the ambient temperature, which is the outdoor temperature, and the system's design. It will typically be higher than the low pressure side. Step 5 would be reading the low pressure gauge. This gauge measures the pressure of the refrigerant leaving the evaporator and entering the compressor. The pressure indicated on the low pressure gauge will also depend on factors such as the refrigerant type and system conditions. It will generally be lower than the high pressure side. Next, you compare the readings. When the system is operating normally, the difference between the high and low pressure readings is called the pressure differential, or pressure drop. The difference is an important indicator of the system's performance. Abnormal pressure differentials could indicate issues with the system. Make sure your hoses and manifold set are rated to handle the refrigerant being used. For example, an old R22 manifold system and hoses are not designed for today's high pressure refrigerants such as R410A. A few notes when servicing refrigeration equipment. It's not legal to flush lines of liquid refrigerant after a burnout. You should always test refrigerant for acid after any possible introduction of moisture into the system. So any repair work where the system was opened up is a potential for moisture. Crankcase heaters are designed to help with refrigerant that's migrated and mixed with oil in the compressor crankcase. It's also used to help cut down on the possibility of oil foaming. When talking about global warming potential, or GWP of refrigerant, CO2 is used as the comparison baseline. It has a value of 1. When dealing with hydrofluoroolefins and hydrocarbons, they have the lowest GWP. HFCs, CFCs, and HCFCs are much higher. And for example, R410A and R22 are thousands of times higher on the GWP scale than a natural refrigerant like CO2. Some of the flammable refrigerants being used today, such as R290, which is propane, and R600A, which is isobutane, have a very low GWP, much lower than HFCs. HFCs have a high GWP and are bad for the environment, which is why they're being phased out in the future. So let's talk a little bit about refrigerant classifications. Hydrocarbons are the least dangerous to the environment with a GWP value of less than 10. Those include what we just talked about, which is propane and isobutane. Chlorofluorocarbons, or CFCs, include R12 and R11 and are the worst for the environment. They contain carbon, chlorine, and fluorine. As you look to the right, you can see the ASHRAE ratings on flammability and toxicity of refrigerant. And what you're seeing a lot in today's industry is the move into A2L type refrigerants, which are your more flammable refrigerants. Hydrofluorocarbons, or HFCs, include R410A, R422B, which is marketed under the name New 22, R134A, which is commonly used in vehicle air conditioning systems in the United States, R404A, and R407C. They do not contain chlorine, but they do contribute to global warming, and they have a low ozone depletion potential. Azeotropes are made up of multiple refrigerants that behave in the same way at a constant temperature, and they are considered a pure compound for that reason. Hydrochlorofluorocarbons, or HCFCs, include R22 and R123. They do contain fluorine, carbon, hydrogen, and chlorine. They're lower GWPs than CFCs. Hydrofluoroolefins include R1234YF, which is used a lot in Europe. They have no ozone depletion potential. They are mildly flammable, and they're miscible with polyol ester lubricants, or POE oils. They do still contribute in a small way to global warming. Zeotropes are blended refrigerants that have different boiling points, unlike azeotropes. Temperature glide can range, may be made of either 2 or 3 different parts of refrigerant. Refrigerant pressures are shown below in the chart. In the low pressure category, you have R123, R1233ZD, R11, R245FA, and these are refrigerants that operate at or below 30 psi at 104 degrees Fahrenheit liquid phase. Medium pressure refrigerants are R134, commonly used in refrigeration applications and in vehicle air conditioning, R600A, which is isobutane, and R1234YF, commonly used in Europe, but it's making its way to the US, operate at 30 to 155 psi at 104 degrees Fahrenheit. High pressure refrigerants include R404A, R410A, R22, R407C, operate at 155 to 340 psi at 104, and very high pressure refrigerants or CO2, or carbon dioxide, 340 plus psi at 104 degrees. Bubble and dew points are used on temperature pressure charts to point out evaporation and condensing temperatures. Dew points are used when charging by suction superheat. Bubble points are used when charging by condenser cooling. Refrigerants should be only replaced by EPA-approved substitutes. Blended refrigerants can leak at different rates. This leaves a different amount of each refrigerant remaining in the system, which is known as fractionation. This can cause issues with refrigerants that have a high temperature glide, such as R407C. 400 series refrigerant should be weighed in as a liquid. When changing HCFC refrigerants to HFC refrigerants, you must remove the alkyl benzene oil and replace it with an ester-based oil, which is polyol ester or POE. POE oils are very hygroscopic, meaning they will absorb moisture very quickly and easily. POE oils cannot be mixed with any other oils. And when you're dealing with these type of things, it's very important that you're checking for acid and that you're making sure to use filter dryers to clean up the system of any moisture content. The subjects of recovery, reclamation, and recycling are very important to understand the differences. To recycle refrigerant is to remove the refrigerant, clean it up, and reuse it in the same or another system owned by the same owner. It can be cleaned through dryers and through oil separation. Recovering refrigerant is to remove the refrigerant and charge it back into the same system or another system owned by the same owner, or turn it into an approved reclaimer. This means that you're pulling it out and you're putting it back in. You're not in any way cleaning it. To reclaim refrigerant is normally done by a manufacturer, although there were old reclaimer machines that were in the industry years ago. And what that does is it cleans the refrigerant and returns it to a like-new virgin state. In order to be considered reclaimed refrigerant, it must meet the AHRI 700 standard. There are two types of recovery methods that can be used. An active recovery system, which is shown on the right-hand side, is a machine that can actively remove the refrigerant from a system, whether the system works or not. A passive recovery system passively catches refrigerant in a running system. You cannot use a passive recovery method in a system that will not operate. It should be noted that any reclamation equipment manufactured after November 15th of 1993 must be EPA certified, and a label stating such certification is required. Recovery cylinders in the industry today typically look like what you see on the right-hand side. They have a gray bottom with a yellow collar on them and red and blue valves to indicate your high and low side. Individual cylinder is needed for each different type of refrigerant a technician is working with. You should never mix more than one type of refrigerant into a cylinder. You cannot sell recovered refrigerant or put it back in any system that's not owned by the same owner that it originally came from. There are various ways of detecting leaks within a refrigeration system. One of the most commonly used is nitrogen. When you're installing a brand new HVAC system, it's common to charge it with nitrogen and do a pressure test on it to see if any of the nitrogen leaks. Second would be a trace gas, where a small amount of the refrigerant being used is mixed with nitrogen to detect leaks with an electronic leak detector. It's important to note that this is okay, and trace gas does not have to be recovered. It can be vented, but it's just a very small amount of refrigerant mixed with the nitrogen. Pressure testing is, once a leak is repaired, a pressure test should be done at the maximum pressure the system is rated to operate at, which would typically be done with nitrogen. All flammable refrigerant should be leak tested and vacuumed down to 500 microns before charging. Vacuuming a system removes moisture from within the system. It can also be called dehydration. Leaving the water content in a system will lead to the development of acid, which can eventually cause system failure. Systems should be pulled down to at least 500 microns, measured by a vacuum gauge, and held there for a period of time to ensure that there are no leaks and the system is completely dry. It's important to note that when you're vacuuming down a system, all refrigerant must be recovered from the system before the vacuum process starts. If not, that refrigerant will be vented to the atmosphere. Vacuum pumps should be connected with the largest diameter hoses and shortest length of hose possible. Vacuum gauges should be connected as far away from the vacuum pump as possible to get the most accurate reading. The amount of moisture, the ambient temperature, and the size of the equipment will affect the length of time that proper evacuation takes. However long it takes, it's a very important step, and it needs to be done properly. Once a system's pulled down to 500 microns, the system should be able to hold that vacuum. If the pressure keeps rising, then you may have a leak in the system. If the pressure starts and stops rising intermittently, there's most likely still moisture in the system and it needs to be vacuumed additionally. Recovery cylinders are designed to hold 80% or less of their rated capacity. This is to allow a room for expansion whenever the cylinder is in heat, such as in the back of a service vehicle. Some cylinders have a built-in electronic float valve that'll hook to the recovery unit to make sure that it's not overfilled. If not, weighing the cylinder while recovering is a good method to be able to ensure that you don't go above 80%. Cylinders must be hydrostatically tested every 5 years to make sure they're safe for continued use. Cylinders should not be damaged, rusty, or allowed to roll around or fall over. They need to be secured properly in the back of the vehicle before they're being transported. Labels should always be used to indicate what the cylinder contains. For instance, adding a label to it or a tag that says that it has 34 pounds of R410A in it. You should never heat a cylinder with a flame, as it may change the chemical composition of refrigerant inside. Refrigerant cylinders that are heated with flames typically have the refrigerant break down into one of 2 or 3 different kinds of acid. Only approved refrigerant cylinders should be used. Never use a disposable cylinder. Whenever you have a disposable refrigerant cylinder such as an R410 or an R22 cylinder, when you're finished with it, that cylinder should be recovered down to 0 psi and disposed of properly. Never refill those type of cylinders as a recovery tank. As mentioned earlier, all cylinders should be labeled so the contents and amount can be easily identified. This helps with keeping the necessary records and helps to avoid mixing refrigerants. Recovery cylinders must be DOT or Department of Transportation approved and must be labeled with a DOT classification tag. When shipping refrigerants, shipping documents such as a bill of lading should have the refrigerant labeled as a hazard class 2.2 non-flammable compressed gas. This is the majority of refrigerants, excluding things like isobutanes and propane. General safety rules when dealing with refrigerant include that refrigerants should not be inhaled. Any refrigerant in a high enough concentration can cause asphyxia and death. When working with a flammable refrigerant, a red coloring is required on all tubing close to the connection. The red must extend at least 1 inch on either side of a service connection in a flammable system. Technicians should be familiar with the safety data sheets or SDS sheets for anything they're working on and have them readily accessible. Always wear gloves to help prevent frostbite and wear safety glasses to protect your eyes. When leak checking a system, nitrogen should always be used. Never leak check a system with compressed air or oxygen. When these are combined under high pressure with oil, they can cause an explosion. Leak testing should never exceed the maximum low side pressure of the system. When using nitrogen, always use a regulator and pressure relief device. Never hook additional pressure relief devices up in a series. If you have more than one pressure relief device, they should be hooked up in parallel. You cannot braze or cut refrigerant lines that still contain flammable refrigerant. It must be recovered first. Make sure all flammable refrigerant systems are grounded before recovering. Do not use open flame around flammable refrigerant or cylinders containing a flammable refrigerant. Flammable refrigerants can ignite if the correct fuel and oxygen ratios are present. Additionally, cylinders that get too hot can result in explosions. What this is typically called is the upper explosive limit and lower explosive limit. When you have the right amount of flammable refrigerant mixed with the correct ratio of oxygen, it can cause them to ignite. If you have too much oxygen or too much refrigerant or vice versa, you won't have that problem. When refrigerants are exposed to extreme heat, they can form acids. Depending on the type of refrigerant, they can form phosgene gas, hydrofluoric acid on a fluorine-based refrigerant, hydrochloric acid on a chlorine-based refrigerant, carbon dioxide, or carbon monoxide. This is another reason that you just don't heat any refrigerant cylinder with an open flame or a torch. One of the primary reasons for the Section 608 is the stratospheric ozone depletion. The Earth's ozone layer is what helps shield us from the ultraviolet radiation from the sun. Many refrigerants have a high ozone depleting potential, or ODP. Depletion of the ozone can lead to damage to marine life, crop issues, cataracts in humans, and an increased risk of skin cancer. The chlorine compounds found in HCFC and CFC refrigerants cannot be cleared out via the rain because they are not water soluble. Ozone, which is made up of 3 molecules of oxygen, depletes when the chlorine from a CFC or HCFC steals one of the oxygen molecules away. The resulting chlorine monoxide molecule then goes on to destroy additional ozone by dropping the extra oxygen molecule to another molecule of ozone, thus making 2 separate O2 molecules instead of an O3 ozone molecule. An atom of chlorine can continue to stay in the atmosphere and destroy ozone for up to 120 years. 1 atom of chlorine can destroy over 100,000 atoms of ozone. The Montreal Protocol is an international treaty designed to cut down on ozone-depleting substances. The United States is part of this treaty. The United States has started the process of discontinuing ozone-depleting refrigerants such as HCFCs and CFCs. The EPA Section 608 of the Clean Air Act spells out the regulations of anyone dealing with refrigerant. EPA certification, Section 608 certification, applies only to persons who are accessing or exposing refrigerants. It does not apply to persons servicing electronics, performing cleaning, or any part of the installation process that does not involve opening up a sealed system or refrigerant charging. A technician must be certified to the level required to work on whatever he or she is servicing. In addition, they must have their certification card physically with them while they are performing the service. Technicians that knowingly release refrigerant to the environment can be fined up to $44,539 per day and lose their certification. Leaked trace gases, as we mentioned earlier, mixed with small amounts of refrigerant can be vented without penalty. Natural refrigerants such as CO2 and ammonia are exempt from the regulation and can be vented. Refrigerant recovery machines must be certified to the AHRI 704 standards. The EPA requires small appliances to have a process stub if it doesn't have service valves. 2020 is the phase-out year for R22, which has already happened, and also R142B. All other HCFCs will be phased out by 2030. After the phase-out, recovered or reclaimed gas will be available for service, but new gas can't be produced. The EPA Section 608 certification does not cover desiccant-based dehumidifiers because they remove moisture by the use of a desiccant and do not contain refrigerant. It is not legal to top off one refrigerant with another, for instance, adding R404 to an R22 system. Refrigerant vented by cutting copper lines or theft, or vented after recovering, is illegal. Records must be kept to document all recovered refrigerant. Those records include the type of refrigerant, the quantity recovered, the quantity returned for destruction or reclaim by month, and the quantity recovered from appliances that are being disposed of by month. In review, you should recover all refrigerants before working on a system. No open flames around tanks of refrigerant. Make sure recovery system is grounded, especially when working on flammable R290 or isobutane. After the repair is made, leak check and then vacuum. Hold the vacuum at or below 500 microns to ensure that all moisture is gone and to also make sure the system is not leaking. You should label and tag all refrigerant, keep adequate records, and always carry your EPA card when servicing equipment. Do not vent any gas to the atmosphere except trace gas or unregulated refrigerants, which are natural refrigerants such as CO2 and ammonia. Recovered gas can only be used in the same system or another system owned by the same owner. Do not top off refrigerants with a different refrigerant. Make sure you're using the correct oil. Always vacuum the system to remove all moisture. Acid test after any major repair. Only use DOT or Department of Transportation approved recovery cylinders that have been hydrostatically tested at least once every 5 years. Only fill the cylinders to a maximum of 80% by using either a refrigerant electronic float or a scale to weigh in the refrigerant. Remember to label and secure cylinders before transport. And do not mix more than one refrigerant in one cylinder. This concludes the core section of the EPA's Section 608 study course. We'll now move on to the Type 1 certification topics.